Well, okay, everyone. Thank you for coming. I think that we can start now. I hope the mic is working fine, and people also that join by Zoom. Okay, that's good. So thank you for coming to this first seminar and this hybrid event, like in person and virtual. Hopefully it goes well. So we are very happy to have today here the Kristin Persson. So she's the director of the Molecular Foundry at the Lawrence Berkeley National Lab. She's also a faculty at University of California, Berkeley. Actually, she's a very remarkable scientist. So she has also the director and the founder of the Materials Project that I believe has been something very successful initiative. She's also the leader of MGI community and applies essentially her research is on the modeling, using data-driven modeling for materials and innovative methodologies. She's also an associate editor for the chemistry of materials, and she's on the advisory board for the NanoHub and Fermat. She has also a number of awards, for example, the DOE and faculty early career. So actually very, very remarkable. So I think that today you are going to talk about the data-driven, and you're going to show us some of your recent research. So what we are going to do after that, we'll take the questions. So I'll try to manage the questions that you have here in person. And then if you have questions on the chat, please write that. I will also try to scan through that. And yeah, without any further ado, please go ahead and welcome.
Thank you. It's my pleasure to be here. I was at MIT for 4 years before I went to Berkeley, so it feels a bit sentimental to come back here and walk in the corridors and getting lost, like we all do. So I'll be talking about data. There's lots of space up here. Feel free. What data does for materials design, and specifically connecting that to the data that we give out through the materials project as well. So data today, data and access to data is power, right? If you have access to social data, you can influence not only what people buy, but also what they think in terms of politics and healthcare. In the realm of material science, data has a complex sort of history. We're not very good at collecting data and making it available to people. It tends to be locked up in industry if it's systematic data sets, or in journals, where it's not very easy to correlate different data points with each other. You have to do natural language processing and then collect it, and that's a process and a research process in itself. So if you look at what people do when they try to use data to design novel materials, it's usually a very tedious and long-term process, where you're frequently recomputing, remeasuring, figuring out if the things you find in the literature are actually still true or they apply to your problem. And when we design novel materials, we typically focus on a few metrics of performance that we think are the most important ones, or the ones that will give us the best publication, right, or the best patent. So let's take an example. If you're trying to come up with a new thermoelectric material, what people tend to do is look for a material with high ZT. Like basically it's going to give you the largest current for the smallest change in temperature. And they are very proud if they can correlate differences in lattices and structure and chemistry to actually maximizing that CT. But let's say that I'm focusing on a particular nanomaterial, because that's where we find most of the higher CTs, and then I implement that in a device, and I start seeing that ZT that I so carefully designed degrades within cycles of thermal cycling between low temperature and high temperature, which most thermoelectrics end up doing. And that could be due to mechanical degradation of the material or interfacial degradation of material. So it turns out that the understanding the thermal behavior of that material and its interfacial reactions may be even more important, or at least as important, as figuring out that maximum ZT. So I think of materials as a chain, and every link in that chain can weaken it. So the material is only as good as the weakest link in that chain, and those chains are those links are properties. And we have to consider quite a few of them if we're going to be successful in bringing a material all the way from the bench into the market, not just one. And that really speaks to data, right? Having information about materials' properties and being able to correlate them across crystal structures and chemistries. So this is where, and we've gotten very excited about machine learning, right? All of my students who come to me today say they want to do machine learning. And I go like, yes, machine learning is a great tool. It's like that beautiful Ferrari that you want to drive, right? But unfortunately, to drive that Ferrari, you need fuel. And that fuel, in many cases, still fossil fuel that has taken the Mother Earth millions of years to make. Or today, you can use maybe lithium-ion batteries if you're lucky. But that being said, in the case of the materials realm, that fuel will take you the longest time to figure out the data. You're going to spend probably, and this is what I tell my students, you're going to spend half a year to a year figuring out how to collect that data, to clean it, to correlate it with features, to figure out what actually matters until you can drive those fancy machine learning algorithms on it. And then they get a little bit disappointed, and I go like, that's fine. We're still going to do the machine learning, but you just have to do the hard work first. And it's boring too, unfortunately. So yes, data is important not just for materials design, but also for doing the new optimized algorithms that we want to apply on that data. And this is where computations come in. So I hear that you guys are all in some way interested in sort of computations. Yes? Data, algorithms, cool. Okay, this is totally for you then. So a little bit on my perspective, personal perspective, I got my PhD in Stockholm many, many years ago in a galaxy far, far away. So when I was a graduate student back in Stockholm, I spent an entire year calculating one property for one element using first principles calculations. Because the computers weren't as fast and the algorithms weren't as mature. I spent a fair amount of time fitting pseudopotentials, parallelizing a plane wave code that was completely new, and a linear response code that had never been tested before. So that took a year. And now, about 20 years later, on the materials project, we have over 130,000 calculated materials with that same DFT methodology. Yes, we have new functionals, we've gotten better, but it's much more plug and play. It's not entirely plug and play because you still need a fair amount of information about how to run those calculations, but it's much better than 20 years ago. So leveraging computing power as well as the robustness of our new algorithms and the ability to solve the Schrödinger equation, we now have millions of calculated associated properties available for free on the materials project, which hopefully is helping us to focus on not just one of those links in the chain, one of the properties, but we can actually now filter materials for many of those properties and focus on the ones that have a larger chance of making it into the marketplace. And that's really the idea of going from the Edisonian approach, where you sort of, it was named after Edison because he tested one material after the other until he finally, years later, came up with one that he said, yes, this is it. But of course, he's limited by time and his prejudice to some degree, right? Because he decided that these are the collection of materials I'm going to investigate. So now we can cast a broader net because we can pre-filter materials. We can calculate in what classes of chemistry and some structures you should be able to find more likely candidates that do not have those weak links in your chain. For example, if you're looking for a new photocatalyst and you are wondering, can an oxynitride ever survive in an aqueous environment where I want it to be stable? And it turns out that no, you can never get to the stabilization energy you need. You can coat it probably, but then you have another set of problems. So those are the kind of questions you can ask of the computer if you can calculate the stability of the material and you can correlate that with aqueous stability. And then you can focus you and your experimental team on the more likely candidates. And this is very much a loop. This is not just one filter, here we go with 3 materials. It's very much a learning curve. And you iterate and you become better and better at understanding what the links are between your properties and your chemistry and your structure and where you need to look. So I was at MIT in 2004 and 2005, and that's where I really got excited about this vision that you can use computations to filter materials and bring them closer to market. We were actually hired by by a company as consultants to find a better cathode for your alkaline batteries that we have pretty much everywhere. They gave us $1 million in a year to do it, and it was the first time we've ever actually done this like comprehensive screening across voltage, capacity, and most importantly, what do you think is the most important property for these guys that you cannot live without? Alkaline batteries. They have to be stable in very, very high pH and KOH. That's much more important than screening for voltage and capacity. It was relatively easy to find materials that were better than the current state of the art, or at that time, manganese dioxide in terms of voltage and capacity. But it was really hard to find materials that were stable at pH 15. So that became the largest sort of learning curve for us, that what we originally thought was the important metric of success turned out to be secondary to understanding stability in the operating media. That was in 2004, 2005. I'll get back to that story. And after that, I got so excited about that I ran off to Berkeley and started the materials project because I thought that, okay, this is what we need. We absolutely need to give data. We had spent a year on calculating all these properties. We had screened 100,000 materials, and we had so much stability data, so much data on materials in general, and we had learned so much. So I thought, this is the way to go. We need to give this data to everybody. And I was able to convince some famous professors from MIT to join the cause too. So it was very much a group endeavor. And since then, these are just examples that are from the materials project or people are associated with it, but many other people are doing it as well. These are examples of materials that were first predicted in the computer using this kind of methodology and later synthesized and tested and shown to work as predicted. So they're real sort of examples of computational successes. Going back to the alkaline story, screening 100,000 materials in 2004, 2005, we gave them 200 out of those that we thought had a better chance that was better than manganese dioxide and had a chance of making it. Duracell spent a lot of time figuring out how to stabilize these materials because, of course, higher voltage and higher capacity usually correlates with higher instability. And about 10 years later, in 2019, they commercialized the optimum battery, which does contain one of those 200 materials. So it does work, kind of, to accelerate materials discovery and design with computations. That being said, new Duracell batteries are not going to change our world. There are more important things to work on, but it was a very important proof of concept to me, at least. So the materials project, we founded it around the vision that, yes, you can do first principles computations one at a time. A lot of people are doing that. But if you're going to do it large scale, it's kind of the same difference as if you were to walk into a restaurant and say, like, hey, I need a table. And if it's not a tremendously occupied restaurant, you can usually get a table. But if you're going to have 1,000 people coming into a restaurant, you just don't walk up to that restaurant. They're going to look at you. Are you crazy? It's the same with high-performance computing. If you're going to launch 1,000, 10,000, 100,000 calculations, you need to be very sure you're doing the right thing. You need to write workflows. You need to benchmark it. You need to have automatic analysis tools and infrastructure. And that's where all this stuff comes in. We have written a lot of in-house codes to manage those calculations, to benchmark them, and to be in dynamic communication with our database, so that when things go wrong, which they invariably do in calculations, we can get help automatically. So it doesn't have to be a graduate student or a postdoc to say, okay, fix this calculation, change the K-point density, up the EN cut for whatever the plane runs you're doing. All those recipes are applied recipe-based and by learning. You can imagine that there's machine learning going on there too, right? What are the best recipes I can now fix my calculation and try and over again? So there's a lot of work going on between this part, the code, to manage these high throughput calculations, automatic import and building of data into databases. We use MongoDB to do that. And we have builders for every single property, and they all have to work together, and honestly, everything breaks all the time. But we're a very small team compared to the Amazons and the Google of the world. And then we use our API to disseminate this and to port that data to the website, and eventually we try to do design with it, it's a few examples, and I'll give you some examples of materials that we developed or that we designed in-house from computations and that were later validated, and I'll give some comments about the bottlenecks. What are the current bottlenecks today? Okay, so accelerated materials design and syntheses. Emphasis maybe on this part here, because this is rapidly becoming the big difficulty in making and designing novel materials. A lot of people think of this as a funnel, and it definitely has a funnel aspect to screening materials for specific properties. If you're going to find a new photocatalyst or a new magnetocaloric out of the materials project, you come up with what are the kind of metrics and properties that I want. You filter on stability, you may be filtering on band gap, electronic properties, and you can literally do that with the API in minutes with the current data. And then you can analyze that data and say, hey, where are the big hits? What are the chemistries and structures that correlate with the kind of behavior that I want? You learn from that, and then you do your own calculations to sort of fine-tune that space and get better ideas. So it's very much an iterative process and a lot of learning going in here. I'm going to take two examples of the ones we've been looking at lately, magnetocalorics and piezoelectrics. So in the case of magnetocalorics, First of all, again, you have to produce your data. We didn't have a ton of magnetic diverse data on the materials project, so we first designed a workflow to calculate, or at least try to track down as a good of an approximation as possible to the collinear magnetic ground state of any material. And that could be any semiconductor, oxide, whatnot, that is in. So again, you have to tune your parameters on how to solve the Schrödinger equation. And we benchmarked that against the best neutron data that we could find. We are disseminating it, but we also try to see, well, now that we have this cool data, can we use that workflow and that data to design a new magnetocaloric material? And what are magnetocaloric materials? Well, they're basically materials where you switch the material between a high-spin ferromagnetic state to a non-magnetic state or an antiferromagnetic state. And with that transformation that you can then use a magnetic field to induce, you get an associated change in entropy, which of course means an associated change of absorbing or desorbing heat. Now, just the magnetic transformation itself tends not to give a large change in entropy, but if you couple it to a structural transformation as well, you get a much larger delta S and therefore a larger delta Q, which means a large change in heat. And you can now start thinking about that material as a solid state refrigeration element that can absorb and desorb heat depending on where in your cycle you are. So Ram Seshadri at UC Santa Barbara, he was intrigued by these properties, and he invented this nifty deformation descriptor that is very easy for us to compute. It's basically just computing the change in volume between the magnetic and the non-magnetic state. Fairly easy to calculate. And then he correlated that with a measured change in entropy for many of the high-performing, and you can see there's not that many, sort of 10 to 15 materials, and so that there's a reasonable correlation here, even for the highly engineered materials up here. So we used his descriptor to look over the materials project, and we screened over, I think, 5,000 materials. And you can see that this magnetic deformation descriptor, yeah, it's, most of the materials, not surprisingly, are down there because you're not going to get a large structural transformation. But there is an interesting or intriguing little collection of materials up here, which of course is where we focus our efforts. And one of the materials that we liked specifically was a manganese antimonide. Why did we like it? Well, I can tell you because it had been made. It was a known mineral. It had been made. There were synthesis recipes for it. But nobody has ever, as far as we could tell, measured its magnetocaloric response. So the predicted property was new. So we predicted that this material would have a large magnetocaloric response. And interestingly, that if you went off stoichiometric in this material, if you started putting manganese not only in their sites, specific sites, but also interstitially, you could tune the on-site temperature, or the onset temperature. So your magnetocaloric materials obviously it's nice if they have a large magnetocaloric response and therefore absorption of heat or desorption of heat, but it's also nice if you can tune the temperature of that switching because you need your material to be active in a certain temperature range. The only problem was, of course, that if you tune the temperature to too low, you also decrease the magnetocaloric response because those interstitial manganese ions actually became antiferromagnetic, so they decreased the overall magnetism of your material. So these kinds of calculations we can relatively easily do now for one material that comes out of the funnel and get insights about it. Ram Seshadri's group made this material and tested it for the different stoichiometries, and indeed you can see both the temperatures tuning as well as the overall heat absorption capability of this material was validated. So it was a good prediction of an existing material that was relatively easy to make because it was already existing, but with new properties. Okay, I'll give another example. Polar behavior. Some years ago, we wrote a workflow for the piezoelectric tensor calculation. It's not a hard workflow to write because there is an algorithm in VASP that calculates the piezoelectric tensor for you. But writing the workflow also, again, includes selecting all the parameters that goes into it for insulators, for semiconductors, all the different classes of chemistry and structures that you have to calculate. And we benchmarked it on can you guess how many piezoelectric tensors there are in the open literature that you can lay your hands on? Full tensors. Give me a number. 10,000, 40, 20, 200? It's 50. 50 full piezoelectric tensors. It gets a little bit better if you go for elastic tensor, then you're sort of in the 200 to 300, but that tells you how pathetic our data availability is, right? From experimental measured piezoelectric tensors. So that's what we had to deal with. Oh yeah, the number is there. Hey, you guys have to help me out here when I'm. So we tested against these 50 tensors, and when we were able to reproduce them without any intervention within plus minus 15%, we were pretty happy with our workflow. And then, of course, what we want to do is try to see if we can design a novel piezoelectric material. We looked at the ones we had. We started filtering them on things like, are they reasonably stable? Do they have a large response? And we were particularly interested in finding something that doesn't contain lead. Because the largest piezoelectric industry today is all around PZT. And it's actually $1 billion industry. And even though the sensors, the amount of material that goes into them is minuscule, there's so many of them that you imagine the amount of lead that goes into our waste stream, just from all the electronics, that waste that we have, it's not small. And it's such an important material that Europe, even though Europe really likes to ban lead and has banned lead for pretty much everything, it has given exception for PZT, just because we don't have a good replacement today. So we were interested to see if we could find something else that doesn't include lead. And there was an intriguing material, a strontium hafnium oxide, a distorted perovskite that came out of our exploration and that had a predicted high response for piezoelectricity. Now, normally, I would not have advocated this particular polymorph for exactly the reason that I advocated the manganese antimonite, because it had never been made before. This was a hypothetical material that is part of our database because we also like to explore substitutions, explore what could be out there that we do not know about today in our natural mineral world. And if you have your candidate stoichiometry and you enter it into the materials project, you can see why this is a particularly challenging idea. So there are not only 1, 2, 3, 4 polymorphs. So they're shaded in green, the ones that have been made on the materials project. So 4 polymorphs that have been made with that stoichiometry in that space. And the one we're looking at is this guy. So it's competing with 3 known polymorphs that are supposedly more stable at the same stoichiometry and 2 hypothetical ones. And all of these guys are non-polar, by the way, so they're not going to do anything for us piezoelectricity-wise. The only reason we still went after it because I had some incredibly brave experimentalists at NREL, the National Renewable Energy Lab in Colorado, that had an interest in trying to see if they could make a metastable material. They were not so interested in the piezoelectric part. They were more interested in saying, can we actually make a material that has this kind of competition in its phase space? And they are experts in epitaxial growth. So we were trying to find together a substrate that would selectively penalize the ones with lower energy and promote the one that we were trying to make. So use specifically this old algorithm from Zur and McGill from 1984 that basically tells you how large do I have to grow my supercell of my target onto the substrate before I'm coherent, again, with the lattice. And the larger that overlap is, the worse my material is going to grow. We can also, because we can compute the elastic tensor once we stretch the material to fit onto the target substrate. And if that energy of that elastic strain is large, then we're penalizing the material. So we use those 2 metrics to come up with our best possible substrate to penalize the lower lying, more stable structures up in energy and lower the ones we were looking for. So we came up with a substrate that was strontium titanate, not too surprisingly, but we also doped it with niobium to get the right polar character of it. It took 2 years for the experimental group to not only try to make this material under the right circumstances, many trials and errors, to grow this thin film on top of that substrate. They first have to make the substrate and then have to grow it, and they tried many times, and then characterize it to the point where the reviewers and us believed that we had indeed made that particular distorted perovskite and not any of the other low-lying, very closely related. And it turns out that, again, this one was also, they confirmed the ferroelectricity as well as piezoelectricity. Full disclosure, if you grow that thin film thicker, it decomposes. It's that metastable. So you have to have a very close epitaxial relationship between your film and your substrate to be able to stabilize it. But indeed, it is a material, it is a phase that can be grown thin and has the right response as predicted. But 2 years, right? The computations in themselves took maybe a week once you actually made the workflow. So 2 years of synthesis and 1 week. Okay. Then there are materials like this one that we predicted some years ago. If anyone can make it, and if there's anyone who knows synthesis in here or does it, feel free to take it and run. It would be one of the most amazing magnesium cathodes in terms of mobility. It has a diffusion barrier that's less than 100 MeV per atom, which we have never seen. We computed it some years ago. We've contacted our friendly experimental people, but because it has a double substitution on the cation sites, they don't want to try it. They go like, no, too risky. So there are examples now of materials that we have predicted new properties of, that are known, that were easy to make, materials that were new, hard to make with new properties, and this one that so far as I know, nobody has tried to make it. So synthesis and characterization is increasingly becoming one of the things we feel we have to make an impact computationally, and not just saying, go make this, but also how and why to motivate our experimental counterparts. So we've spent a fair amount of time the last couple of years to try to sort of advance the science of synthesis by computational means. So not just doing this funnel here or this sort of exploration, but also if I have a target, can I come up with a set of recommendations such that it has now also, I can filter out these guys in terms of likelihood of making them. And I'm going to address two things. Is it likely to be synthesizable, or at least can I rule out the really bad ideas? And selectivity. Can I suggest precursors that would be more selective towards this particular target? So first on the synthesizability, here is a plot that Wenhao Sun made a few years ago, which does statistics of the ICST, so that's the known compounds. They actually do contain theoretical compounds too, but most of the inorganic known compounds in the world, crystalline. And it correlates how many there are as a function of the energy above Hull. So the energy above Hull is the sort of our reigning stability metric. The Hull is made out of the stable compounds in a particular composition space, and the energy above that, it tells you how metastable or unstable a particular material is, because it's going to basically release that energy if it decomposes into the Hull compounds. So energy above Hull, basically the higher you are, the more unlikely you are to be stable, but it's a very fuzzy metric. So you can see that it correlates, right? There are many compounds known that have been made and synthesized that are below 100 MeV per atom. So we could put our screening criteria at 100 MeV per atom and say, like, anything above that, we're just not going to recommend to our experimental counterparts. But as you'll see, you will miss some, right? It's not a complete metric. And this is for oxides. If you now include nitrides and chlorides and other kinds, and you separate them out, you see that you get about 80%, well, 75% of all known oxides if you put your screening metric at 100 MeV per atom. But for nitrides, you only get to 50%. So clearly, there's a much larger tolerance for metastability in nitrides than there are in oxides. And you're not capturing that if you're putting your level or your screening metric on just one number. So we wanted to do better than that. We started thinking about, well, how does synthesis happen, and what is your competing phase space? So let's say I want to make a particular polymorph of tantalum nitride for no good reason whatsoever, except that I could find what the nice precursors was for tantalum nitride. So for tantalum nitride, you use tantalum oxide and ammonia. And when you're mixing those precursors together and you're heating it up, you're breaking bonds, right? What are you going to make? Are you going to make a nice crystalline polymorph, or are you going to make amorphous gunk, which is sort of your competing stuff here? Well, you should always be able to kinetically make amorphous gunk, right? Because as soon as you start breaking the bonds in your precursors, that's basically it. That's already there, amorphous gunk. So kinetically, amorphous is fine. Whether you can make this one is still up for grabs. So we started thinking about thermodynamically. How does the amorphous state compete with your polymorphs, your crystalline polymorphs? And if you look at the enthalpy, so your Gibbs free energy at T equals 0, and we hypothesize two polymorphs, B and C here, that are lower in enthalpy than the amorphous state, but polymorph A up here is higher in enthalpy. And because the amorphous state is so disordered, it should have a much larger configurational entropy, which means that its slope of dg dt at constant p should be much larger. It's sort of liquid-like, right? So polymorph B and C has sort of a window of thermodynamic opportunity being lower in Gibbs free energy, but polymorph A does not have a shot, does it? It's neither thermodynamically favorable, nor is it kinetically easy to access. So the amorphous state, we can say here that we are hypothesizing that there's an energy limit, a fundamental energy limit for polymorph synthesizability set by the enthalpy of the analogous amorphous state. And the good news is we can actually calculate an approximation of the amorphous state by using quench melt in the computer and then getting to the right density for a particular pressure, taking several snapshots, and then calculating the enthalpy of that amorphous state and averaging it. It's probably an upper bound because nature will find a slightly lower version of that amorphous state. But at least an upper bound will do it for testing this hypothesis. So we tested it over 44 systems with different stoichiometries and different chemistries. And the bars here are set by that amorphous limit. And you can see how different it is, right? Going from carbon to nitrides to oxides, there's a huge variability from 50 MeV per atom up to 900 MeV per atom, depending on the system. And this really starts to teach you a little bit about why we have found such amazing polymorphism in some materials or some chemistries, but not in others. So looking at boron oxide, for example, boron oxide has these little sort of tetrahedra, and doesn't really care how those tetrahedra are organized, if they're nicely organized in a crystalline lattice, or if they're all jumbled together. So the amorphous enthalpy is actually rather low, which gives you a very low window opportunity for metastable materials. But boron nitride likes these very ordered covalent bonds and hates being amorphous. So that means that the amorphous enthalpy is going to be really high, and now you see this large number of polymorphs and structures that now can survive, right? Because they're not competing with that really low-lying amorphous state. And of course, the skyscraper, right? That's our carbon system. That's why we have all these buckyballs and nanowires and nanotubes, because amorphous carbon is very unstable, so it gives a very large window for metastability. And that explains, again, the sort of nitrides versus oxides, right? Oxides are more tolerant to being amorphous. Nitrides hate it, so there you go. You're going to get a lot more metastability. So if you're off looking into some cool nano material, like something, go and look and see what the amorphous limit is first, because it will give you a much wider opportunity. So that gives us a way to get away from these one matrix fits all, which is clearly not very good at figuring out where are the opportunities. And somewhat of a screening for at least the bad ideas. Just to give you, this is silicon dioxide, and all these guys up here, can you guess what they are? They're basically zeolites and MOFs and COFs and all those things that have a very porous network and need some sort of liquid to stabilize them. If you just try to do it without it, they're all not going to be synthesizable, and you're going to decompose them to the amorphous state. We call this the synthesizability skyline, because it looked like the Chicago skyline, and because the postdoc who did this work was from Chicago, or did his PhD there. All right, so that was on some idea, at least an upper bar for synthesizability. And now I'm going to address selectivity in the last sort of scientific part of my talk. So this is a little bit more complicated. Again, I've talked about the convex hull, which we use as a metric very often to think about not only the metastability of my compounds, but also the competition of the other things that can be made in that space. If you talk to experimentalists, they very often think in this picture. Like if I'm trying to make a compound, a target, I have my precursors, and here we go. Here goes the lowering delta G, and I have some kinetic barriers, and I'm trying to tune that trajectory. So we try to think about, well, how can we phrase our thermodynamic landscape in something that will allow us to compare what they're thinking with our ability to calculate things. So we created this graph network that has the same ability of finding the lowest path in thermodynamic space between a set of precursors and a target. And if you do that for the materials project, you get really hairy graphs like this. they're like huge. The nodes here are compounds, and the edges are reactions. And it's like miserable. It's millions and millions of possible reactions. So we needed a metric to score them. We used the total delta G for any path, and the soft plus function to rank them, so that we get a nice, clean way of ranking one path over the other. And then you can use nice mathematical algorithms like Jens and Dijkstra's algorithm for finding the shortest, that means the lowest energy path for between a set of precursors and your target. Okay, so that's on the framework. This allows us to take the materials project and put that into a framework that thinks about the sort of precursor to target roadmap. Now, selectivity. Let's think again about our convex hull and how we want to interpret selectivity. So here I go between vanadium and sulfur, again, for no good reason except that it looks nice. If I blend vanadium and sulfur and I heat it up, solid state synthesis, very classic, I'm most likely to make this guy here because it has the largest delta G driving force between my two precursors. However, once I've made this guy here, I'm going to create interfaces between the vanadium 3s4 and the sulfur, and the vanadium 3s4 and the vanadium, right? Because I have these particles, they're reacting at the interface, I'm making a new phase, I now have two more interfaces. And once I have two more interfaces, I now look at two more chord lines in my convex hull, and now I have driving forces for making other stuff too. So now I might make vanadium s4 here, vanadium 5s4, and vanadium s4. So if you think about it in more sort of illustrative, here I have vanadium particle, sulfur particle, they're reacting at the interface. I'm largely probably going to make, it's all about kinetics too, right? But if you just think about the thermodynamics, this V3S4, now I have two new interfaces, and I might make other things too. So this is a case of high driving force. I took the elements because I got a large thermodynamic driving force to make my target, but I have low selectivity, because there's a lot of other competing phases in that space, and they'd be made under other kinds of interfaces. So what if I do something else? What if I try, I want high selectivity instead, but in this particular case, that's also going to mean low driving force. Let's say I take my two closest polymorphs, these two guys here, and I blend those in my crucible instead, and I heat it up. The only way they can lower their Gibbs free energy is by combining to form this guy, right? That's the chord rule again. But now I have really low driving force. I have high selectivity. It's the only thing that can possibly make. It's probably going to take months of very high, or some amount of temperature before I just like melt the whole thing or whatnot. But at least it's very highly selective. So in many cases, you're dealing with this competition between selectivity and driving force. So we were interested in looking for systems or synthesis methods where you can to some degree decouple these two, because we think we have a metric of selectivity, thinking from how to parameterize your convex hull. So your convex hull, again, now we're used to this picture here, but if you phrase it in terms of chemical potential instead, which is always a bit of sort of, okay, chemical potential, remember your thermo, right? It's basically the slope of your convex hull. So if you cast, I plot the chemical potential of sulfur on one axis and the chemical potential of vanadium on the other one, and this is my window of chemical potential for my target, my V3S4 that I want to make, and I want to make it selectively. Then I can calculate what is the difference, what's the distance between the chemical potential from my one precursor sulfur down to my target, and my other precursors, vanadium, up to that target. And if that's a large distance, it's very likely to correlate with competition in phase space. But if I'm starting from these guys here, or these guys, then I have much smaller distances in chemical potential to my target. So we're basically going to say that distance in chemical potential between your precursors and your target is a measure of selectivity. The larger that minimal distance is, the worse selectivity you have, because there's going to be other competing phases that you are going to make. So we're going to test this on a real system, and we were, again, very fortunate to have great experimental collaborators. This comes from Jamie Nielsen's group, and they have been focusing on metastasis synthesis methodologies. And why is metathesis so great for this particular problem? It's because metathesis uses spectator cations and anions to add thermodynamic driving force to your reaction. And spectator, by that I mean they do not contribute to the product. They just create something else and basically say, okay, now I'm getting extra delta G just because. So I'm, to some degree, maybe I can decouple the driving force from the selectivity. So in this case, we're combining alkali carbonates with yttrium chloride and manganese oxide. And depending on which alkali I'm doing this with, I'm forming and temperature, I'm forming 3 different polymorphs. That's really intriguing, right? Isn't it? Like the alkali that in the end doesn't end up in your product tells you which one you're going to make. That seems like a great way for us to test. So at low temperature with lithium, you make the perovskite. At low temperature with sodium, you exclusively make the pyrochlor. And at higher temperature, you only make the hexagonal, no matter what alkali you're using. So we're going to ask ourselves, there's lots of things to unpack here, and we've tried to do it all. But in this particular talk, I'm only going to talk about why does the pyrochlor only form with sodium? Why does lithium and potassium not do it? So we ran our network, and we calculated all the lowest paths by delta G, ranked by the soft plus, and this is very hairy. So I'm just going to say that these 2 paths here were indeed exactly what the Nielsen group found by using in situ XRD during the synthesis of the process, with lithium as well as with sodium. This one here is actually very similar. The only difference is you're making yttrium oxide instead of yttrium oxychloride, and it turns out that that one has just really bad kinetics, which we do not incorporate in our model currently, and we wouldn't expect to find it. So of the 3 highest ranked paths, 2 were exactly the right match, and 1 was very similar, and we couldn't capture the difference. What I want to highlight here is that in both the sodium and the lithium case for making the pyrochlor, we have a specific layered intermediate, lithium manganese oxide and sodium manganese oxide. So clearly that is something you have to make first in order to get to that pyrochlor structure. And when we analyze, and this is now in chemical potential space, oxygen, manganese, and lithium, the distance in chemical potential space between that intermediate, clearly necessary phase, lithium manganese oxide, and sodium manganese oxide, you can see what a much larger sliver sodium manganese oxide has compared to lithium. And you're trying to get to this pyrochlor phase up here. And this one has a nice overlap. So minimum chemical potential difference, a metric of selectivity. And it really tells you this one is going to have a really large distance, right? And this one is going to have a very small one. It's actually a mathematically interesting concept of how to measure the distance in surfaces in multidimensional spaces. We end up doing it by the vertices because it's actually not a trivial problem. So if anyone here is mathematically inclined, feel free to think about it. Okay, so this was lithium, this was sodium. We actually now corroborated the fact that sodium manganese oxide should be very selective towards making the pyrochlor because it really nicely correlates with that chemical potential distance. This was an after the fact sort of understanding because the Jamie Nielsen group had already made all these compounds. We're now testing it whether we can make it in a forward predictive fashion. So we're giving them synthesis recipes with new precursors for materials that have been really hard to make in the past and see if we can make them. So stay tuned for that. All right, so again, minimal chemical potential distance, very large, no selectivity, and this one very low. And if you now want to combine the two, so minimal chemical potential distance, you want to be low here, and large driving force in delta G, so you want to be large negative here. And we checked over 3,000 possible reactions, including all of these possible precursors, and you can see how really excellent sodium is using this metathesis reaction that has a large amount of delta G, as well as a very highly low chemical potential difference to the target phase. So we really do believe that making these maps will be a great future tool in trying to see what should be the best precursors for solid state synthesis for materials. All right. Okay, I'm getting close to when I think we should wrap up for questions. So I'm just going to end with the sort of vision of how, or the excitement really about what this kind of data will do for not just my group and my research and my collaborations, but also for the community. I think we have to get increasingly better at sharing our results, not only in journals, but also in ways that are more codified, that people can easily access and correlate to other data items. And this is what the Materials Project does a lot better than has been done before. So we have all this data, and we have focused not only on crystal structures, but also on properties of materials, because in the end, that's kind of what we want, right? Crystal structures will only get us so far. And we have a large number of varying amounts of data. This is really just a few of them. And as we talked about, elastic tensors, piezoelectric tensors, and dielectric tensors, now orders of magnitude more data than was in the open literature before. Computed, yes, not experimental. We do rely on that experimental data to get us to that point, though, to validate our workflows. To give you an idea of how machine learning, because I talked about that too, ties into this, once you have 13,000 elastic tensors, you can do machine learning on them. You can correlate the crystal structure, the local environment of your lattice, and your chemistry with your elastic response. So if you go on the Materials Project and you look for a specific material and you want this elastic tensor, don't give up. You actually click this button, and then out comes a guessed machine learned estimate of at least the Young's modulus and the shear modulus. In the case of our XFs and Zanes spectra, again recognizing that synthesis and characterization are rapidly becoming things we have to accelerate as well as just the prediction of the material, we've computed L-edge and K-edge Zanes and XFs for over 50,000 materials. And that's also, again, now enough to do machine learning. So all of those spectra are now available online. You can correlate them with the local environment in pretty much any material you've made. Amorphous, nanocrystalline, whatever, crystalline, because it's only sensitive to the local environment and the valence of your cation or your anion, as well as its local coordination. And if you upload a spectra, you have no idea what it is except that you know the chemistry. Like, I know it's a manganese oxide, but I don't know what it is. You can now get a machine learning estimate of what kind of crystalline structures that looks most similar to that one based on our data and the algorithms. And it's exciting to see what people do with this. So currently in 2020, we have 1 paper per day published that cites the Materials Project for machine learning. Basically, they use machine learning for something that they're doing. And that's 1 paper per day, and it's like, you can see, it's like going a bit crazy here. And it's really cool to see how other groups that have nothing to do with us are using our data. So here are 2 examples of groups that have developed new phosphor materials and new super hard materials. And these are, again, validated by experiments. They've actually made them and tested them. And the data, it's the data they've used, some of the data, not all, they may have developed their own as well, comes from the Materials Project. So again, hopefully we will all become better at this. We have over 200,000 registered users. Somewhere between 5,000 and 10,000 people log into the site every day. But maybe most excitingly, our API serves between 2 million to 45 million of spikes of data records every day. I've rapidly become not just a material scientist, but also somebody who like manages a software center, because we had to scale this up with different servers that have to spin up depending on the demand of the downloads. Sneak peek. We are working on a new website. It's going to be even better than the current one, with a number of new available data sets as well as analysis. It's actually up, but somewhere in this next coming year, we're going to swap it with the old website. So if you're using the Materials Project today, stay tuned. You can actually test this too, and please send us feedback if you like it. We're currently very actively developing it. We have a number of new apps. We have a synthesis explorer based on NLP of synthesis recipes in the literature. Hopefully the stuff you just saw on the chemical potential distance or stuff like that will also come. We have the catalysis explorer and the MOF explorer, which I'm so happy to say comes from the community. We didn't do the calculation. So people have come to us and say, please, I have this enormous data set that I've spent like 5 years developing. I really think it should go into the Materials Project. And we've worked with them to make that into a community sort of, dissemination. So it's used all over the world. We're very excited to see, especially in places in the world where maybe you don't have the same kind of journal access data that we take for granted. California used to be banned by Elsevier. Do you remember that? That was rough. So there are places in the world where people use the Materials Project as the resource of citing, this is the material I'm working on. They can't actually access the journals because they're all behind paywalls and stuff like that. So I think we need to get better. And I really want to thank my group. It's amazing, and without which I wouldn't be able to do any of the things I do or to stand here and talk about today. And I'll be happy to take questions.
Thank you, Kristin, for such a nice talk. So yeah, we are going to be open to questions now. So yes, please raise your hand if you have any question. Yeah, go ahead.
Yeah, so in one of your slides, great talk by the way. In one of your slides, you showed sort of a graph connecting all the different materials in the database, like the reactions between them.
Yep.
Where did you get the reactions from? Like, was it from the literature, or did you like enumerate what all the possible reactions?
Yes, but not from the literature, from the Materials Project. So you can build
Maybe,
this.
Kristin, if you don't mind repeating the question for the
sorry.
people at the
Okay.
yeah.
How did I come up with the reactions, the edges in that graph? So using just the Materials Project, we can build any reaction, right? And we have the energies for all of our materials. So like you say, manganese plus oxygen gives manganese oxide. We have the energy for manganese, we have the energy for oxygen, we have the energy for manganese dioxide, so we can now actually build that. So we don't need the literature for that part. And that's how we build a network. Every possible reaction between every possible compound in the Materials Project.
I see.
Yep.
Okay, I can go with a question in the chat then.
Sorry, I'm going to not direct this. You're going to direct this.
So from the chat, you mentioned that this is important to think material discovery as a multi-objective problem. My understanding is that materials in MP come from ICSD. Is it necessary to explore materials beyond ICSD because there might be no materials in ICSD satisfying the multiple properties that you want to optimize? And can we explore unknown materials?
Yep, that's a great question. I don't have to repeat that one, right?
I think that
because you're okay. Good. So we actually do have a lot of what we call hypothetical compounds in the Materials Project, a growing number of them. The ICSD, maybe, I'm going to guess here, 20, 30,000 of our materials of the total 140 are hypothetical. So they're not in the ICSD. And it is a growing number because every time we do an exploration of a phase space, we typically do substitutions, and we always add those to the database as well. And I agree with the person who asked the question that I do think it's an exciting phase space to look into. Again, beware of the competition, right? The strontium hafnium oxide is an example of such a hypothetical material that, yes, in the end we could make it, but it's not. It took 2 years. So, yeah.
Now, maybe Nicola, you can go ahead.
Yeah, so very nice talk. How do you deal with uncertainty in computation experiments? Because you're getting data from all over the world. And usually one needs to get and read the paper and see what did this person do, what did they approximate, what's their uncertainty, oh, this is completely wrong, right? So you are accumulating all of that data. How does quality control work?
Yeah, no, that's a great question. So number of different checks and balances depending on where the data comes from. So for example, I'll take one example. When we calculate the energies of our compounds, of course, we're trying to use the best practices of how to solve the Schrödinger equation with DFT for the different classes, insulators, metals to semiconductors. That being said, there are different uncertainties associated with these classes. For example, we tend to do phase stability reasonably well, but we say, well, within 20 MeV per atom, we don't really know. Band gaps, we're abysmally bad at band gaps. So, and we know that. And we actually put some of those warnings on the website. There's a known problem with DFT that we are particularly bad at getting the stability of things like gases, molecules. So whenever we're correlating phase stability to an element that is gaseous, like oxygen, sulfur in its molecular state, we're even worse. So we've built in statistically algorithms or assessments of how much we need to correct for the DFT energy based not only on what our typical distributions look like, but also what the experimental uncertainty is. Because we're always correlating that back to what is the measured enthalpy of that reaction. And if we know that, yeah, we're wrong by X number, but you look at 3 different measurements and they're off by a little bit. So we're trying. The earlier version of the Materials Project didn't have that. We just sort of took 3 measurements and tried, it's like, okay, that's going to be good enough. But we are building in uncertainties, and we're also trying to educate our audience. Because if you're an experimentalist, and I actually had this feedback on the materials project, one guy emailed me from Sweden, no less, telling me that, oh, your band gap of gallium arsenide is like listed as 1.3. I happen to know it's 1.35. And I go, like, that's amazing. That's so good. But he was very upset because he thought this was theory. It should be absolutely spot on. So educating our community, because computations are new, right? I think experimentalists are used to thinking in terms of uncertainty for their experimental data, but they don't know where the goalposts are in computations. So we have under every one of our phase diagrams or our band structure diagrams, and like DFT really underestimates the band gaps for most inorganic materials. So at least, I mean, everything from half an EV to an EV. So I think it's both an educational process as well as trying to build in those uncertainties. I can go on, it's more, but hopefully that gives you an idea.
A question from the chat. Can the materials project predict plasma chemistry reactions?
Ooh. Well, first of all, it's not my expertise, so I would probably have to sit down and talk to somebody who does that before I get an idea. But anything high temperature, you sort of have to think very carefully about the entropic contributions. So that's what we do when we did the solid state reactions that I just showed in the metathesis. That is anywhere from 600 degrees Celsius to 900 degrees Celsius. We're building in the machine learned vibrational entropy into that. We can't deal with the configurational entropy because that's hard. So I'm assuming that that's going to have to be an issue, as well as kinetics. I'm assuming also that, whatever the, yeah. Okay. So I'll have to talk more to that person before I can give an intelligent answer.
Yeah, so kind of tagging off
Mm-hmm.
what we talked about with the band gap problem with DFT.
Yep.
So are there efforts right now to just do things like hybrid functional calculations, or is that feasible for the kind of scale that we're talking about? Hundreds of thousands of materials,
yep.
Or like where do you see that going in terms of better properties?
Totally love better functionals.
So the question is how to scale up, I suppose, all this very large database of reactions.
Well, yeah, and getting better.
Yeah,
getting better methods.
Yeah.
So you're absolutely right that better methods tend to correlate with higher compute time. Hybrid functionals are more expensive. We're actually in the process of recomputing the entire materials project with R2 scan, because it's a much better functional for the polymorph energy difference. The hybrids are better for band gaps. We haven't seen that they're better for stability, and a lot of our analysis on the materials project goes off of stability. So what we tend to do is that we use our PBE, GGA, or GGA plus U ideas of band gap, and then we recompute it with a hybrid. And that data actually isn't on there, but we have hybrid calculations of band gaps for probably something like 5,000 materials. We just haven't been able to put it on. There is actually, though, band gap contributed from a group in Denmark that has done another functional. So yes, absolutely. It should be built in. It's just a question of compute time and people. Yep.
Hi, very nice talk, thank you. I have a quick question regarding the defects in materials.
Mm-hmm.
In your talk, you mentioned in magnetocalorics, like interstitial size
yep.
can play a role, and that's doing in many other applications.
Mm-hmm.
So just wondering how the materials project approach those defective materials, because I guess all those non-symmetries or interstitial size can really expand the space
yep.
significantly.
Yep, great question too. So we do have algorithms and workflows both for non-charged as well as charged defects. We have developed that, so you can address it in a fairly sort of plug and play. Charge defects are hard, but we've gotten there. It took one graduate student several years to make sure that he had all the right parameters. But you don't do it for thousands of materials. You don't build Brouwer diagrams for thousands of materials. It's just too expensive still in terms of calculations or like compute. Although I gotta say, right, if you want to advocate for me, like get Google to put their compute power behind it, we can totally do it. It's still like I'm using maybe 1% at best of NERSC, which is like the largest one for DFT calculations in the US. Because there's all these annoying people running combustion calculations and climate simulations and those things. But so if you really think that material science is the thing, we should all we can do it. But given the compute time that I'm getting, I can't. So what we tend to do is going down that funnel, right? So you screen your materials problem all the way down to like, okay, now I've got 100 materials or 20 or 2. And then you can do those extra expensive calculations and hope that that isn't something you should have put on the beginning, because then you've lost your screening power. Yep.
So it is already one, so maybe we have time for one more question, and then we just wrap up. I think you wanted to ask? Yeah, go ahead.
I was wondering, like, if you want to add new properties or like calculate new functionals for the database, how do you prioritize which molecules and things to look at first?
Yeah, we tend to, if we don't have a specific application that we're going after, sometimes a student comes with an idea like, I want to look for, spin spirals in nickel oxides, right? And then we go after, of course, the nickel oxides. But if you have no reason for it whatsoever, we tend to go with energy above hull, because we want to fill up from the bottom, right? We want to get that property for the things that are most likely to be synthesized, and then go up in metastability space until one day we'll hit the buckyball, right? Or whatever, right? It's up there. So that's usually how we prioritize. Yep. But in terms of functionals, again, we're a small team, right? We're four staff that are permanent, and one web developer, one programmer, and 2 software materials engineers. And the rest of my group is doing it for free, basically. They're graduate students and postdocs that come with funding and just love being part of it. So in the end, we're nothing. We're like a mini startup trying to do this. So we do it as much as we can. And if somebody comes in and says, we absolutely have to do this today, we go like, well, either you really advocate for it or you come with funding. So we can put more people on. Yep.
Okay, so well, thanks a lot, Kristin, again, for this terrific talk. Thanks to all of you for coming in person and also for the people who joined. We'll see you next time, and I think it's next week. Yeah, the next seminar is going to be next week. So.